welcome all of you to PQI 2020 or the PQI 2020 fall poster session, Quantum 2020. So my name is Jenny Stein. I'm one of the executive co-directors at PQI along with Chao Zhou. So you've probably heard a lot from either him or me over the last few months or in the last year. So the theme for today's event is spooky action at a distance. We wanted to have something that sort of folded in both quantum entanglement, because that's Einstein's description of quantum entanglement, something that reflected that Halloween was in a few days, because it's spooky, and also the fact that we're all at a distance because we're not allowed to meet in person and breathe on each other. So normally this would be the Science 2020 event hosted by Pitt, and we'd all be in the alumni hall probably. But they actually decided to pause their event because of COVID. So we still wanted to hear from all of you and hear about your research and have an opportunity that you could all, get together in one room and see and learn from each other. Because I know it's hard to develop new collaborations when you're not sure what everyone's doing and you're all stuck at home anyway, or two to three people per lab can come in. So it's difficult to connect in this kind of time. So I just wanted to introduce our judges and then go over the rules really quick. And then if there are any questions, I'm happy to answer those. Feel free to unmute anytime and ask because we're a small crowd. So I wanted to welcome Mason Shamanzer. I think he's a faculty member in CMU's Department of Electrical and Computer Engineering. Hopefully he's able to connect soon. If not, maybe he's just hiding out. Our other judge that would be coming and hopefully will is Wang. He's, I think, a staff or faculty member, not really faculty, at the Pittsburgh Supercomputing Center here in Pittsburgh. And then our previous poster award winner judge is Singi Gan from the Department of Chemistry at Pitt. So as you've noticed, we do have a diverse crew of people from different backgrounds and very interdisciplinary. So that's why we sort of emphasized try to be accessible in how you describe your research, because you might be talking to a physicist or a chemist or an engineer or a programmer, who knows, computer scientist. A lot of different people want to learn, and it's hard to do that when you speak different languages. So for the rules, you'll each have 3 minutes where you'll share your screen, and I'll post the link to the agenda so that you can sort of be aware when you're coming up next, but obviously I'll let you know when I want you to share screen and if you're next. Over that 3 minutes, go ahead and give your presentation. At 2 minutes and 45 seconds, I'll give a visual cue. I'll just hold up something red. So I have this dragon here. So I don't like interrupting, but at 3 minutes, if you're not in your conclusions and final outlook section, I'll give a verbal cue to wrap it up. After that, we'll open up the floor to judges or anyone here, peers, or maybe we'll have a random audience member to unmute and ask questions. But I will try to also keep to time with that for 3 minutes. And then judges, Mason, if he's here, Singi, I know it's a lot that you're going to have to listen to someone talk, come up with questions if you want to ask them, and also evaluate a poster. Hopefully you have the link to the poster grading form in front of you. But if it is hard to keep up and click submit and then submit another, I'll send the recording to you after, and you can always, we've got till Sunday at midnight if that works to get your scores in by then. Okay, I think that's all I want to say. Does anyone have any questions? No? Okay, well, I'm really glad that you're all here. Hopefully my judges will show up. But if not, it'll be a little bit quieter, but they will eventually score your session. So I think we're starting with Kshiteej. I'm sorry, I messed it up. You're first.
No, that's fine. Yeah.
Katie.
Should I go ahead?
Yeah, I think we'll go ahead and get started just because, yeah, I don't want to wait. I don't want to keep everyone too long.
Okay.
That's good.
Yeah, can you see my screen?
Yeah, your audio is a little bit staticky, but it's overall works well.
Am I clear now? Yeah.
Sounds good.
So, I mean, should I start? Just start?
Yeah, I
Oh,
think.
okay, yeah, sorry.
Yeah. Go through.
So hi everyone. Today I'll be presenting my work on bond energies of molecules using the strictly correlated electron limit of density functional theory. Now, in my introduction, I'll just tell you quickly what the strictly correlated limit is. Now, conventional DFT starts by making the approximation that the system is weakly interacting, that is, the electrons are weakly interacting. You can go to the other limit and say that, okay, what happens if the electrons, if I start from a limit where the electrons are strongly interacting. Now, this assumption applies well to the systems where electrons have strong interaction, like, for example, system in molecules where you have bond breaking, there the electrons are strongly interacting. And our hypothesis is this theory, which starts with the strong interaction limit, will perform well for such systems. So what we have here is, instead of focusing on the minimization of kinetic energy, if you can see my cursor, what we are going to do is focus on the minimization of electron-electron interaction. But obviously, this minimization is a very difficult problem. It's in R3n. So what we do is look at a concept in math called optimal transport. Now, in optimal transport, it's a problem which was studied long ago, where you wanted to minimize the cost of transporting mass from one domain to another when you have a cost of transportation associated with the path you're taking. So if we try to adapt that to this problem, then we have our Coulomb potential as the cost function and the electron densities as the equivalent of mass density. And what you're now trying to minimize is this cost of transportation. So you do the math formulation, what you get at the end is a nested minimization and maximization approach. So you have this functional g of v here, which is your minimization, and you put that in here to find the electron-electron interaction energy. And this is your nested optimization problem. So when you have this functional sorted out, you put that in the Kohn-Sham equations. You want to solve your Kohn-Sham equations by putting in that electron-electron interaction functional in there. Now, the potential that corresponds to that functional, we refer to that as the Kantarovich potential, which is denoted by this u rho of phi here. So you solve the system self-consistently and arrive at the ground state energies. Now, in literature, this is a very new area, and so the most the results that have been obtained are for an hydrogen molecule. So our first step is to look at what the energies of the hydrogen molecule is using this theory. So here, the figure on the right shows the work in literature where they compare different theories, like different Kohn-Sham models used, like LDA, B3-LIP, and they plotted out the bond energy curves. But you see that the one in the blue asterisk here is the one by the strictly correlated electron limit, and that is very accurate in the bond breaking regime. So what we do is
come closer to the end soon. Sorry, we're running out of time.
Okay, yeah. And so in our work, we compute the same values with the LDA and with the strictly correlated limit, and we see that our curve matches exactly with the exact curve using the strictly correlated theory. We perform these results for the hydrogen molecule. We have here the density contours and the Kantarovich potential. Now our plan is to go and explore higher dimers. Like, for example, I've shown here a carbon molecule. And what we have found is then a smallest ansatz shows that it is not able to reproduce the bond energy curve, but you go on using more approximations in your ansatz, and you're able to reproduce at least a curve that qualitatively looks like a bond energy curve. And this is a continuing work, and as we increase our approximation, we hope to obtain better and better bond energy curves. So for this, we use finite element formulations to write the code And that's a numerical tool basically. So right now, yeah, this is the stage of our work right now. Thank you.
Right. Thanks, Katie. Are there any questions from the audience or from judges?
I have a question.
Yeah.
What is the benefit for doing this where you were studying the bond breaking regime? Why not studying, why do people just not stop at studying DFT?
Studying the what?
So like, why do you need to get a better approximation for the bond breaking regime?
Yeah, because like a lot of people the interest arises because when you are looking at theories like, for example, in polymers, you do not have in continuum. If you come from a quantum mechanics perspective, you do not have good approximations for what the failure theories are. So this is like an attempt to study it at the most fundamental level, and like since because the conventional Kohn-Sham methods have this weak interaction assumption, so this is just another approach where you say, okay, let me start from the strong interaction limit, and we see that it's more accurate in the bond breaking regimes where you are pulling apart things.
And instead of showing a dimer of the same elements, can you show one that's like a positive negative interaction, like an oxygen hydrogen interaction?
I mean, that's something I can do, but yeah, I've not tried it yet because yeah, it's at a very nascent stage yet. So yeah, first, I mean, the plan right now is just to try a few dimers, like, explore the periodic table up to the first few elements.
Thank you.
Yeah.
Are there any other questions from other presenters or one judge? If there aren't, that's okay because we've got time that we need to catch up on. So thank you very much for your presentation and for your Q&A section. If you want to stop screen sharing, our next presenter is Dina.
Yeah, hi. Okay, let me pull this up. Okay, can everyone see that?
Mm-hmm.
Cool. Okay, so hi, my name's Dana Peirce. I am in the physics department at Carnegie Mellon, and I'm going to be talking today about growing this topological Dirac semi-metal sodium bismuth on an antiferromagnetic insulator. So this is an in-progress project, so mostly I'll just be reporting on the fact that, hey, we've done this growth. But before I do that, I just want to talk about why do we care about growing this heterostructure? What's the interesting physics we want to see here? So over here in this graph, figure 2, you can see, okay, so just a bulk 3D Dirac semi-metal that's characterized by linear dispersion in 3 dimensions, and we have band touching at a Dirac point. So that's sort of like, those are the 2 main things that make something a 3D Dirac semi-metal. And then you can see if you confine your semi-metal in the Z direction, basically by making it thin, you can see a quantum spin Hall state. But then further, if you induce magnetic ordering into this thin material, you can see the quantum anomalous Hall effect, where one of the spin edge channels on the side is suppressed. So you get this like anisotropy on the edges. And so this would be, if we're trying to show this by proximity effect, which hasn't been seen before. It's been done before by doping, which is another way to introduce magnetic order into your system. However, it's less controllable and it's not reversible. So when you ultimately have your eyes on devices, this would be a better way to do it. And we're on our way to doing that. So now we can talk about actually doing our growth. So the main things that we care about when we say, okay, we want to see a good growth, well, what does good mean? One thing is we, of course, want to see the crystallinity of sodium bismuth and chromium oxide, which is the antiferromagnetic insulator that we chose. And then we also really care about flatness. We need, in order to get this proximity effect, we need to have really good smooth interface between our materials. So here in figure 3, you can see sort of a time lapse of read images, which are read is reflection high energy electron diffraction. So if you're not familiar with how to look at these images, you can basically think of it as a diffraction grating. You're essentially having diffraction off of your crystal. So a more uniform pattern means you have a better order of crystallinity. And these are good read patterns. We're really happy with these. So first off, that's just something you can do to characterize during growth. We also have XRD. So here we have a chromium oxide peak, and these are Lau oscillations on the side, which just show that we have highly ordered layers in our material. This is for chromium oxide. And then I know I'm running short on time, so I'll just say we have some AFM images, which basically we're essentially at the noise level for what our AFM can detect. For chromium oxide, we have a RMS roughness of less than 100 picometers. So we have a really flat film, and moving forward, we're going to do magnetotransport measurements on these samples. And sodium bismuth is sort of hard to work with because it's air sensitive. So you're sort of limited as to how you can characterize it ex situ. You have to basically do everything in vacuum. But so far we've grown this heterostructure, and right now we're moving towards doing some other measurements on it. So we're excited about that.
Great, thank you so much. Great work. Anyone has questions, and so I welcome people other than judges, since we do have a small crew, to pipe up. There's no such thing as a dumb question, so we're all unfamiliar probably.
So
Was that someone?
That was
yeah, that was me. Can you hear me now?
I can hear you now, yeah.
Yeah, I'm using my tablet and my computer. Thank you. Nice start. So I have a question. These diffraction patterns, are these like diffraction of X-ray from the crystal, right?
They're it's electron diffraction.
Electron diffraction. Yep. So can you please explain how this measurement is done? What tool have you used? And
yeah, so you basically have this beam of high energy electrons. We have 15 kilo electron volt beam, and it hits your sample at a low angle, so usually between 1 and 5 degrees. And then I've sort of covered it up with the labels, but underneath where these would, you would see a really bright spot, and that's just the specular reflection where most of the electrons just reflect, but some of them diffract up at a higher angle. So some of the things you can look at to sort of see, to characterize your read image is uniformity in the height. So when you hit your sample, if you're hitting like a curve, that will essentially correspond to a different intensity in the upper motion, in the sort of like up and down direction of the image. But yeah, basically the electrons that are diffracted just hit a screen, like a photoluminescent screen.
Maybe a quick follow-up question. Are you concerned at all about the lattice mismatch between different layers?
Yeah, so the lattice mismatch between chromium oxide and sapphire, which is our base, is about 3%. And then the lattice mismatch between sodium bismuth and chromium oxide, you actually have sort of like a 30-degree shift between them to get optimal spacing, so it's a different structure, but it's also, it's like 2%. So yeah, we specifically picked chromium oxide because it had good lattice matching with sodium bismuth.
Thank you.
All right, if there aren't any other questions, thank you, Dana. I think we'll move on to Henry. If you want to share your screen.
Sounds good. Okay. Is everyone able to hear me clearly?
Yeah.
Okay, great. That would be great.
That's good.
Okay. Yeah, I'm gonna actually start. Hi everyone, I'm Henry. I'm from University of Pittsburgh, and today I'm going to talk about the impact of solvent identity on our monolayer electrolyte deposition. So EDL gating has been used for doping semiconductors with electrolytes. However, these electrolytes are actually more than 100 nanometers thick. Our group has been focusing on scaling the electrolyte on the D direction. This can provide benefits such as like fast switching and lower power operation. On the right, this is actually the structure of our monolayer electrolyte called cobalt chrome ether phthalocyanine. And this molecule actually lays flat on the 2D semiconductor, and it will have a high and a low resistance state. So the schematic of our experimental design is also shown as here. And on the right side is actually the amazing result achieved by my colleagues, and it shows that the offset can be stabilized, and also the on and off ratio can increase by 4 orders of magnitude. While these results are extremely exciting, one area to improve is the uniform deposition of the monolayer, which I have been actually working on for several months, and also is a requirement for maximum gating. So as the AFA image shown as here, the deposition with acetone actually didn't give a uniform surface. So I dig into the literature and find out that even though our monolayer electrolyte was pretty new, chrome ether binding with ions has been studied actually for decades for wastewater treatment. And the tendency of forming the complex in certain solvent is quantified as the log K value, and the mechanism is as shown here. So I found out that acetonitrile, acetone, and nitromycin all have a higher log K value than ethanol does, which ethanol is our current recipe. And which means that these like 3 solvents actually promote the composition of lithium ion and 15 chrome 5 ether better than ethanol does. So after several experiments with monolayer electrolyte on tungsten dicyanide and analyzed under AFM image, I found out that acetonitrile and acetone are both promoting the complexation. However, acetone is showing to be the better solvent than ethanol and acetonitrile based on the quantified surface roughness and also the line scan, which this high change is consistent with our published work. So also like acetone actually wets the chip surface completely after COCRPC deposition, unlike acetonitrile, which does not. The insufficient coverage of acetonitrile on the chip surface causes small aggregates as shown in this AFM image. So research that has been done actually decades ago and in a completely different field help us today to promote the complexation for further electrical measurements. So my future work will be focusing on exploring additional ions and chromes. And for example, 15C5 actually have combined with sodium and calcium ion. And there's a list of chrome ether we can look into. At the end, I want to acknowledge that this work is funded by the NSF Career Award and also ASSS. And also thanks University of Pittsburgh and PQI for this presentation. Thank you.
Thanks, Henry. I'll open up the floor to questions.
I have a chemistry question. I don't know if you have some ideas here. So for these crown ethers to be sort of deposit, how do you envision that coordination environment looks like on the tungsten diselenide?
So because the molecule is like this, so the phthalocyanine actually, when we basically is drop casting it, and it give like an environment before we actually drop casting, we sonicating it, because these molecules, have like a really high like a steric effect, which may causing like aggregation. So we have to use like sonication to break up all these like small aggregates in the solution, and then we put like a drop casting it and let the in here I use acetone, which is evaporated, and it will leave on the surface as a flat one because that's kind of energetically favorable, but it might be actually having like a stacked, like for example, like this ones. So we will do actually annealing at like 240 degrees, which using like kinetic energy to help it to move to the most favorable like a structure, which is laying flat on the surface.
Okay, thank you.
Yeah, no problem.
Any other questions from audience or judges?
Yeah, maybe I can ask like a high level question. So you mentioned that this material can be used for detecting electric fields, right? Can you elaborate a little bit more? What is it special about this material that makes detection of electric field more efficient?
So basically, I think, so you want to ask like why this material actually help to, under electric field, it will actually be better than most of the other things. Okay, yeah, so first of all, like actually this here, EDL gating have been famous for like actually it's a high carrier density, which around like 10 to the 12 or even sometimes can be 10 to the 13. And also like it's fast switching. Actually from my colleague, they are actually demonstrating nanosecond switching. So which means that we're like increasing like our switch on and off devices more quickly, since the electrolyte was like only a nanometer thick. That's another like advantages. So when the like lithium are toggling back and forth, since the distance is shorter, so which means that will has a faster like switch on and off. And since like right now we're using backgated because we're trying to see which is plus and minus 30 volts. When we actually have a top gated design or even side gated, it might having a low power operation. So which means that because the gate was like extremely close to the channel, WSE2 channel, so which means that it will have a like a lower power operation, less than like when 1 voltage. Since it's actually sub-voltage operation like predicted by our collaborators.
Thank you.
No problem.
All right, well, that actually puts us right at time. So thank you, Henry.
Thank you.
And now we've got Dakota.
Sorry, I need to stop this. Yeah, thanks.
Okay.
Okay. So my name is Dakota Folmsbee, and I'll be talking about my recent work evaluating thermochemical machine learning methods. So our motivation for this work is to determine how well machine learning methods predict non-equilibrium bond stretches, as well as torsional barriers. We set out to test this through 17 bond stretches and 5 dihedral scans for a number of different machine learning methods. For bond stretching, we had roughly 4 criteria in this case. We had mean absolute percent error of the energy in the potential energy well. We had whether or not the machine learning method is predicting the equilibrium bond length to be the lowest energy, whether bond compression results in a repulsive wall, and whether or not we're getting the anharmonic bond stretching that we lose with methods like force fields. What we found through this is that the ANI methods, FCHL, and the convolutional neural net that we've been using demonstrated the best ability to sort of satisfy all of these criteria. So we wanted to look more qualitatively at these potential energy curves. What we see in this case, most of these machine learning methods here are doing a pretty decent job at predicting the energy well as getting our anharmonic bond stretching out to roughly 2 angstroms. One thing we do see is that these machine learning methods tend to start struggling as we get to longer range interactive forces, and in some cases actually decrease in energy total. One other thing that we kind of wanted to demonstrate, we have this sort of edge case in this situation, but H2, a common quantum toy model, we wanted to see, okay, there are no hydrogen-hydrogen bond motifs within the training set. How well is machine learning going to infer this information if it's not in the training set? And kind of what we see here is that machine learning is not able to pick up any of this stuff. Sort of a be careful what you throw at machine learning if it's not in the training set. We also took a look at some 2D torsional scans. Looking at them, we see that the ANI methods qualitatively best match up with our DFT methods. ANI2X had actually additional torsion sampling, which did allow for it to lower the mean absolute energy, making it a more quantitatively viable method as well. We have the convolutional neural net. While it didn't perform quite as well with some of these low energy torsions being over-predicted, we do imagine that passing it, additional torsion sampling should help. From this insight, we see that one of the best paths forward for machine learning to truly become a surrogate for these time-consuming calculations is a much more robust training set. The addition of long-range attractive forces, as well as additional bonding motifs and additional atoms as well. Thank you, and if you have any questions, please let me know.
Thanks. I actually had one question to start off because I'm not as familiar with computational methods, but with machine learning, because you have this training set, does that mean it's supervised?
Yes.
Okay.
Yeah. We ahead of time we gave it a training set in order for it to learn, and gave it the energy values to learn on.
Okay, because I feel like I see a lot of people saying like, oh, well, it's unsupervised now and it learns so much better. So how would, if you switch to unsupervised learning, would it be able to predict things better?
So in this case, unsupervised learning, it's more of, so supervised learning is more of like a K through 12 education where you sit through and the teacher tells you something and then you try to repeat that for the test. Unsupervised is more like undergrad, where you get a bunch of things thrown at you and you kind of have to make out what's important. So there definitely is a place for unsupervised learning. I think at the moment though, while we're still trying to figure out what early on we need for machine learning and chemistry, going more the supervised route is probably the better way to go.
Yeah, it doesn't seem like, yeah, you need to graduate first. Okay, thanks.
Dakota, I have a question for you. How does this, I guess, as an experimental chemist, like how does this help the experimentalist like design sort of like anything that we can do in the lab that you guys can learn from machine learning? So this is more like organic chemistry?
At the moment, this is just super basic, trying to get out an idea of how we can then, how it performs so that we can take it to more application. One thing in our group that we want to be able to do is, have some sort of large search method. So say, chemical space is massive. We want to search through chemical space to find energy storage material. Trying to get hits to decide whether or not we should go into the lab to actually make these. Using like DFT is really time consuming. So if we can use something like machine learning where you're getting predictions in like 1 to 2 seconds, we can really like not quite brute force, but go right through chemical space to find possible good candidates to go into the lab and make. As for the inorganic side, at the moment, most of this is organic. There are a lot of issues trying to get, especially some more of the electron interactions that happen with coordination, the metal coordination, but some effort is being put into that.
Thank you.
Thank you, and I think that's our time. So thank you very much for your presentation and answers. Now we're moving on to Devin.
Okay, can you hear me?
Yeah, you're a little bit quiet, but maybe speak closer to the microphone.
Is this better?
Yeah, thanks.
Okay. Let me just get a pointer here. Okay, can you see this?
Looks good.
Alrighty. So, sorry, just a second. Okay, starting now. Today I'm going to discuss part of a one electron model that we're currently developing, where we're trying to identify molecular analogs to image potential states found on graphene. So image potential states occur when an electron is captured far from the bulk of a solid by a self-induced attractive potential composed of dispersion type correlation between the surface electron and the excess electron. Non-valence correlation bound anions are molecular analogs in that they're also stabilized by electron correlation, and they reside in these diffuse orbitals that are far from the frontier. In our model, only the excess electron is treated quantum mechanically. The interaction with the molecule is handled via classical potentials. The crucial component of this potential is the polarization, where in this case, we're treating each atom with a charge and inducible dipole that respond instantaneously to the perturbation of the excess electron. Charges flow from atom to atom, and you could think of these as sigma electrons in your sp2 hybridized network of carbon atoms, and the inducible dipoles handle the pi electrons. What we want to evaluate is whether or not this polarization model can actually replicate the image potential one expects in something like graphene, which is typically characterized by this -1/4z, where z is your vertical separation between the electron and the surface, in scaling these finite clusters to the size of something like graphene. So what we're actually studying here are these polycyclic aromatic hydrocarbons. They're just hexagonal in shape, and we just grow them out. They follow pattern of C6n squared, where n is just the integer counter. We also study these bare carbon clusters, which are directly analogous. We just remove the hydrogen atoms. So the first figure here, what we're trying to evaluate is how our polarization is performing in replicating the static dipole polarizability using charges and dipoles, as well as just inducible dipoles in our model. And we have reference Hartree-Fock and PBE0 results. What we see is that to capture the polarization of these finite molecules, we're going from benzene up to tricircumcoronene. We need to include charge flow to get the in-plane polarization correct. We miss about 40% when we're just using inducible dipoles, which some force field models use only inducible dipoles. So that's interesting in itself. This is also echoed in our image potential plots, where we see that the inducible dipole results when we scan a negative point charge above the surface of these bare carbon clusters. We actually end up underestimating the interaction severely. Whereas in the case of including charge flow, we see that we get much closer to this -1/4z result as we scale the size of our clusters. However, we're still missing about 13 to 30% of the interaction we'd expect. So that indicates we need to go to much larger systems, say of like 100,000 carbon atoms, to actually replicate this, to extrapolate correctly to the infinite limit. And I think that's time.
You can summarize really quickly.
Oh, sure. So yeah, basically all we're seeing here is that the charge flow is crucial to replicating the polarization in these systems. And for our current model, we're doing pretty well in replicating the finite polarization response. If we want to see what happens as we extrapolate further, we're going to need much larger sheets to actually do so. And that's pretty much all I have to say right now.
Thank you. Open up the floor to questions. I actually have one quick question.
Sure.
How do you scale from looking at something that has like 15 carbon atoms or so here to what I see in your conclusions and future work to 25,000? Like, what's the scale of that calculation time?
Yeah. So this method is actually like n-cubed scaling, where we're using a signed DVR grid. So you get around some of the computational expense of handling something like an actual ab initio calculation. There's also some tricks like fast Fourier transforms that are applied to the kinetic portion to speed things up. However, in terms of actually calculating these, we're using model results that we get from ab initio calculations on smaller polycyclic aromatic hydrocarbons. And we basically scale those to a large enough size that we see a convergence in the property of interest that we're going to use as a model for the infinite system.
Okay.
Yeah.
I see. Thanks.
Yep.
In terms of in thinking about sort of the calculations that you're doing, I know that like in some of the graphene literature, like some people are more interested in like sort of these holy carbons or like nitrogen dope carbons. Like, can your calculations sort of incorporate nitrogen atoms in here?
So there's nothing worked into it right now. I mean, it's feasible if we were to say parameterize our data, our ab initio data for systems where we do say include nitrogens or say holes in it. That is feasible. But the way the model is currently constructed and what we're currently after right now, no, we're not necessarily able to handle that.
Thank you.
Yep.
All right, are there any other questions? Because if not, we'll move on. So speak now or hold your peace. All right, thank you, Devin. Now we are moving on to Chao. Nice accessory. Working in the lab, I see.
Can you guys see my screen?
Can you speak up a little bit louder? I can see your screen. You're just a little quiet, probably.
Okay. How about now? Is that better? Okay.
That's better.
Thank you. Hi, everyone. My name is Chao Zhou. I work with Professor Michael Hytrich at University of Pittsburgh. And this is our work on the design and realization of a quantum state router. So first of all, what is a quantum state router and why do we want to build it? So a quantum state router is the key part of a modular structure quantum computer. And it enables the communication between different modules. Each module here is a lot of qubits that are each coupled with each other, and the qubits in different modules will do the remote communication via this router. And this structure here is very different from the more common seen surface code structure, where qubits only couple to their nearest neighbors. So this modular structure has a lot of advantage over this surface code structure in terms of both modularity, of course, and also algorithm efficiency. So in our design, the router will work based on this parametric photon swap gate. The Hamptonian of this gate is like this. We have 3 modes coupled with each other by this special G3 term here. And now if you pump the middle mode at the frequency difference of the other 2 modes, then photon swap will happen between these 2 other modes. Let's say we put 1 photon in the B mode at the beginning. Then if you turn off the pump at half of the swap period, then the information that was in the B mode will be swapped into A mode. If we turn off the pump at 1/4 of the swap period, then an entangled state will generate between A mode and B mode. So based on this idea, we design our router like this. We pick a quantum device called snail, which has this 3rd order term in its Hamptonian, and then we put the snail inside this waveguide. The waveguide naturally got a lot of agent modes inside it, and the E field of these agent modes will couple to the antenna of this snail. Then due to this coupling, we will have all the 3rd order term inside the system. So now let's say you want to swap information between A mode and B mode. You just pump the snail at the frequency difference between them. Then the information swap will happen. So this is the design of our router. And to prove that this router really works, we couple some simple cavity modules onto this router and try to swap photon between the cavities. So here is the experiment result. We can see that let's pick cavity C4 and we put some coherent state photon in C4 and we turn on the pump between C4 at the frequency difference between C4 and C2 and mirror C4 and C2 at the same time. From the result, you can really see that the photon is really swapped back and forth between C4 and C2. And we also prove that the multiple swaps process can happen simultaneously. And our current work includes trying to increase the fidelity of the swap gate and also try to put real qubit into the module and to have and create entangled state between the qubits. Thank you.
All right, thank you so much. I'll open up the floor to questions from judges or audience members. The free-for-all on anything.
I have a question, if I may. Thank you for the very nice work and nice presentation. Can you please give us some numbers, like what's the difference between these frequencies? I assume the baseband frequency of light is not changed much, and you're talking about modulation of light around the center wavelengths, right?
You mean the frequency of the modes or the frequency difference between the modes?
Yeah, first of all, what's the difference between the frequency of these different modes?
Yeah, so the frequency of each mode is like in gigahertz level, like I think 3 to 7 gigahertz. And the frequency difference between them is like also several gigahertz. And we have to make sure that the difference of the frequency difference is at least 100 megahertz away from each other, so that when you pump one process, the other process will mess up with it.
What is the wavelength of light itself?
The what? Sorry.
The wavelengths of light.
Oh, the wavelength of the light. I think it's in what?
I mean, this is, if I understood you correctly, this is an optical system, right?
Yes, yes.
So what is the color of light, or the carrier frequency of light, or the wavelengths of light? If you want?
The carrier frequency is gigahertz level. So gigahertz.
So it's not really light, right? Because
Yes.
light is like several terahertz, like 100 something terahertz is visible light, right?
Yeah, this is more like a microwave tone, like to be more precise.
Oh, I see, I see.
Yeah, a microwave mode.
Oh, so this operates at the microwave frequency,
Yes,
right?
yes, yes.
Okay. Thank you.
Thank you.
Thanks. Are there any other questions from audience or? All right, if not, thank you very much.
Thank you.
Love the colors of your poster. Thank you. So now we'll move on to our last poster. Yuhei, you look like you're ready.
Yeah.
Okay.
Okay, hello everyone, I'm Yuhe from University of Pittsburgh. I work with Professor Jamie Levy. The title of my presentation is the thermal power of quasi-one dimensional quantum wires at the lanthanum strontium titanate interface. So the system we're working on is this lanthanum strontium titanate interface. Both are insulators, but when around string cell of lanthanum lumen is deposited on top of strontium titanate, we have a conducting interface, and we can tune this interface to conducting state or insulating state. So based on this property, in our lab we developed this conductive FM lithography. So basically with positive tip voltage, and we move on the surface of lanthanum lumen, we can create nanowires at the interface, basically, and with a negative tip voltage, we can erase nanowires. So this allows us to create various nanostructures. And previously in our lab, we have been able to create these electron waveguides with nice plateau structures at the quantum conductance value. This shows the nice band structures, and all these electron waveguides show a lot of interesting properties. But we want to move a step forward before we focus on electric transport. And thermal transport is also refurbished by all these nice electronic properties, and it can be a good probe. So we want to explore that possibility. So that's what we are doing here. So this basically shows our experimental setup. This is for the characterization of the electron waveguides. It's just pretty typical four-terminal measurement configuration. And for the thermal transport measurement, we source current on one side of the nanowire to heat up the nanowire on this part, and this can create a temperature difference across the electron waveguide, and we can measure the induced thermal voltage across the electron waveguide. And since we saw the current sourced is at a frequency of omega, we measure the induced voltage at a frequency of 2 omega. Here we show we have nice high quality electron waveguides, and with that we can measure the things. The thermal voltage, and we can see this thermal voltage is very correlated with the band structure, and based on this measured thermal voltage, we can estimate electron temperature, and we can deduce Seebeck coefficient, which is compared to the other result, to the previous results. Since I don't have much time, I want to end with that. So I hope, so basically our result demonstrate the capability of measuring the thermal power in our system, and we're excited to start from here, and with this as our tool set to explore more fascinating electronic properties. Yeah, that's it. Thanks.
All right, thank you for the presentation. If there are any questions, anyone can feel free to ask this time.
I am going to ask a very silly question. I was wondering if you can explain what I'm supposed to be looking at with the figure that you're showing here, the A, B, C, and D.
Oh,
what am I supposed to take away from this?
So actually in this figure, there are two devices.
Okay.
So so one is from device A, the other one is from device B, and the A and C are the conductance of this electron waveguides. And basically you can see like this, like SiC basically means there's a plateau layer, and it's at the 1 E square over H, which is like the quantum conductance value, which means we have nice ballistic conducting channels in our wire for our electron waveguides. And on B and D is this derivative of this conductance with respect to this chemical potential value. And so you can see if this is a dark region, that means it's at the plateau value, and that's why this value is 0. And this bright area is between two plateaus. And yeah, with this we can see this very nice band structure showing up, and you can see this band sometimes pairing up together and split, and there's some other reentrant pairing with other band space, and this is due to the attractive electron interactions exist in our system, and this suggests there are even like bound states of multiple electrons.
Okay, thank you.
Are there any other questions?
Yeah, maybe a quick follow-up question. So can you please explain how these images and figures that we're talking about were measured? What is your measurement system here? I didn't get the point.
Sorry, I don't quite understand. You want me to explain the measurement? What I'm measuring here?
What I mean, you are showing a 2D map of the conductance of the electron waveguide, right? I wonder, how did you measure the conductance at different points?
So for characterization of these electron waveguides, this measurement corresponds to this configuration here. So we source current on one side and measure. So we basically source current through these electron waveguides and measure the using this 4-terminal technique to measure the voltage across the electron waveguides at the same time. So we get current and voltage at the same time. And so conductance is given by the current divided by this voltage. Yeah, conductance is given by current divided by voltage. And also we have this psi gate. So so basically we can change the this Seagate value to get this plot. I don't know whether I answered this question correctly.
And are you also changing the temperature as well?
No, we keep temperature at the basically at the constant value, but we sweep magnetic field. So all these plots are from 0 Tesla to 9 Tesla.
Oh, so B is in terms of Tesla. I thought when you had T parentheses, you meant like you're changing temperature and you're measuring magnetic field. Okay. Yeah, thank you.
You're welcome. Thanks.
All right, so thank you to everyone. That's the end of our session. So I wanted to thank again all of the presenters, and thank you to the judges that I know you were probably juggling a million things. So thank you very much for coming here and watching and participating. And hopefully, you know, we'll have an in-person event sometime in the next 3 years. Who knows? Thanks. All right, bye.